Okay guys, DNS Exam 3, problem number 42. Remember, this is a calculator question, although as I'm looking at the answers, none of them have crazy decimals in there, so I'm not certain that we're going to need the calculator on this one. Remember that on your calculator questions, maybe only about half of them actually require a calculator. Okay, let's see what's going on here, guys. Problem says here that a rectangle inscribed in a semicircle of radius 8 has one side lying on the diameter of the circle. What's the maximum possible area of the rectangle? Okay, so there's a lot going on in this problem right here. Let's take a look. What are we going to draw here? We've got a rectangle inscribed in a semicircle. So I'm going to start with the semicircle here, trying to draw something that looks like this. All right, and they told us here that the radius of that semicircle was 8. Okay, so this distance from here to here is going to end up being 8. Not sure this is relevant, but obviously then the diameter is going to end up being 16. Look at me remembering some basic geometry. Okay, and a rectangle is now going to be inscribed inside of that semicircle. And we're trying to get the maximum possible area of the rectangle. Well, as you guys may recall, there are problems with going too extreme here. I wouldn't write this down if I were you guys. The problem with this rectangle here, which is very wide but very short, is that the fact that it's short means it doesn't have a very big area. Likewise, if I made it as tall as I possibly could, maybe something like this, well, now it's too skinny to have a really big area. So usually it's something kind of in the middle here, guys. And the location of one of these points right here, probably this one in the upper right, really becomes kind of the linchpin to getting this problem done. So what I'm just doing here is drawing a rectangle. I have no idea the dimensions of this rectangle, but trying to draw a rectangle that's inscribed in that semicircle right there. And again, going back and reading the problem, one side of that rectangle is lying on the diameter of that circle. And they want to know what the maximum possible area of that rectangle is. Okay. Well, everybody gets mad at their math teachers for nerding up problems right here, but unfortunately, guys, this is a floating dot problem, whether you want it to be or not. And a floating dot problem is one where you try to assign a coordinate system to what's going on here to describe the location of the points and everything around us. So what I just drew there horizontally was an x-axis, and then this one right over here is going to be a y-axis. And if we were looking at it in this manner, actually, you know what? I think I'm going to undo what I just did right here. I think it would probably be more beneficial not to let that black dot be the origin, but rather to move our origin right there to the center. So let's try this again. So still we've got a horizontal axis here that I'm going to call x, and our vertical axis here then is going to be y, going right down the middle of this figure. So that's what we're dealing with right here. And then at this point, everybody, the key information right here becomes coming up with the coordinates of this particular point right over here, this upper right-hand corner of our vertex, which is located somewhere along that purple curve, and we've got to try to figure out where it is in order to do this. Okay, so what we're dealing with here, in case you guys haven't put all this together yet, is an optimization problem, the type of thing that we did towards the end of Chapter 4, right before we took our first semester final in December, and boy, that seems like a really long time ago. So we've got to try to come up with our optimization problem, expression right here. And if you remember how to do this from way back in the day, there were a couple of steps to it right here. The first thing we had to do is to figure out the parameter, which was the relationship between your two variables right here, x and y. Well, in order to do that, we're going to realize that that red dot has to be located somewhere on this semicircle right here. So coming up with an equation of that semicircle is essential to getting this one right. And that's why I thought it was a good idea then to move my origin of this system right here to the center of that semicircle rather than having it over here on the left. I think that still would have worked, but it probably would have been more difficult. So what's going on here, guys? We know that the equation of the entire circle centered at the origin would have been x squared plus y squared equals your radius squared. Well, our radius is 8, so r squared is going to be 64. It's generally advisable for us, though, to get that solved for one of the two equations right here. So we're going to solve this for y. And if you guys will permit me to kill two birds with one stone right here, y is going to end up then being the square root of 64. And the first thing we would have done then was subtracted the x squared from both sides. Now remember that technically, because we undid a square with a square root, there should be a plus or minus in front of that radical. But the minus would just give us the bottom half of this circle, which we're not interested in at all. So since we're really just looking at the top of that circle, I'm going to leave the plus or minus out and just go with this. So what we have right here in purple, everybody, that is the equation here that gives us the top half of that circle. And since this red dot right over here has to be located on that semicircle, this in effect right here, everybody, is the parameter. That's step one. Okay, step two in this process here was to write an equation for the quantity that you're trying to optimize. Okay, our goal right here, if we go back and read the problem again, was to find the maximum possible area of that rectangle. So we need an expression here now, guys, for the area of a rectangle. Well, don't try to think too hard and bite off too big of a bite here right at the beginning. Let's just go with something basic. Area of a rectangle is base times height. And now, we'd like to try to figure out what's going on here in terms of x and y. So when we go back to this magic point right here, its x coordinate is x. That is the distance you would travel from the origin straight over here to the right to get to this spot. So this piece has a length of x. But because of the symmetry of the rectangle, there's an x here as well, and the entire bottom side of that rectangle is going to have a length of 2x. So that becomes our base. And the height of that rectangle is the distance we would travel from this point straight up there. That's just going to be a y. So 2xy is the area of that rectangle. However, we'd like to take advantage of the parameter that we came up with right here to get this expressed just in terms of one variable, which we can do pretty easily now. So area, solely as a function of x, is going to be 2x. And then in the place of the y right there, we're going with this. So it's 2x times the square root of a 64 minus x squared. And unfortunately, guys, I think that is as simple as we're going to be able to make that expression. So now I think we're ready to move on to step 3, which is to try to go ahead and differentiate that, and then we'll set it equal to 0 and solve as we move a little further along. So tell you what we're going to do, because I'm almost out of room on this slide and I don't know how to extend here on the iPad. So I am going to take, I thought I was going to take those ideas right there. We're going to copy those. I'm going to go to a new page right here, and we're going to start off by pasting right at the beginning here. Okay, so there's our a of x expression. And let's move on to part 3, guys, which is to try to take our derivative now. So a prime of x is going to equal, and this derivative, because it has two separate factors to it, is going to require the product rule. Okay, first factor is going to be a 2x, and then times the derivative of the second. So this is going to get interesting. We're going to have a 2x. The derivative of the second part, you might want to think of this as 2x times the 64 minus x squared to the 1/2 power. So the derivative of that second part is going to be a 1/2. That 1/2, we'll put a 2 on the bottom, then a 64 minus x squared to the negative 1/2. That gives us a square root on the bottom of 64 minus x squared, and let's not forget the chain rule, times the derivative within, which is going to be a negative 2x. And we'll put that up in the numerator as well. So that's the first part, first factor times derivative of the second, plus, this one's much easier, the second factor times the derivative of the first. That is just going to be, let's see, the second factor is just the square root of 64 minus x squared, and the derivative of the first is just a 2. Okay, so that's our derivative right there. It does look like we can do a little bit of cleaning up right here. We've got a 2 on the top and a 2 on the bottom. They're going to cancel each other out. Unfortunately, guys, that's really about it. So the numerator of the first term is going to be a negative 2x squared all over the square root of 64 minus x squared, and then a plus 2 times the square root of the same radicand, 64 minus x squared. Okay, that's about the best we can do for a prime of x. And now at this point, I think we're ready to move on to step 4. And I tell you what, just to save a little space, I'm going to do that right here. And step 4, was to take that derivative right there, set it equal to 0, and then try to solve that mess. So let's see what we can do to clean this up. All right, anytime you have two ugly terms like this, added or subtracted and set equal to 0, we're just going to take one of them, in this case the negative term, and bring it completely over here to the opposite side. So we're going to get a 2 times the square root of 64 minus x squared is equal to, now it's going to be a positive 2x squared times the square root of 64 minus x squared. Okay, we're going to do a couple things here. I'm going to divide both sides by 2. That'll just get those 2's right there to cancel out. I'm going to multiply both sides by this denominator, which puts it in the numerator over here on the left. So the square root of 64 minus x squared times itself is just going to give us a 64 minus x squared. And that is going to equal the x squared we had over here on the right. Let's take that negative x squared from the left and ship it off to the right. That is going to give us, let's see if I can cram this on the bottom line, a 2x squared is equal to a 64. We're going to divide both sides by 2 to get an x squared is equal to a 32. We're going to take the square root of both sides now and get x is equal to, and that square root of 32 that you would have gotten by taking the square root of the left and the right, okay, you do have to do this by hand. That 32 becomes a 16 times 2, so this is a 4 times the square root of 2. They cut you a little break right here. That value right there is not one of the 4 choices. It wouldn't have surprised me if it were. But the big thing I asked you guys to do at the end of optimization problems is to make sure that you have answered the question. The question here is, what is the maximum possible area of this rectangle? So to answer that, we're going to go back to this formula that we have right over here, guys, which was our area expression, and we're going to evaluate that when x is equal to 4 root 2. And at this point right here, if you wanted to use your calculator, I would understand if you did, but hey, where's the fun in that? All right, so let's see if we can't wing this thing. So we're taking our area function and evaluating it now for an x value of 4 root 2. Okay, so a of x was equal to 2x times the square root of 64 minus x squared. So we're going to have a 2, and the x is now going to become a 4 root 2, so there's your 2x, multiplied by the square root of 64 minus, here's your x value, squared. Now the 4 squared is 16, the root 2 squared is 2, that's going to be a 32 right there. All right, so what happens here? The 2 times 4 root 2 is going to give us an 8 root 2. That's going to get multiplied now by the square root of 32. A couple of different ways to do this, but since I'm trying to do this by hand, probably the easiest thing is to multiply root 2 times root 32 to get root 64, which of course equals 8. So the 8 times the 8 is going to get us a maximum possible area of that rectangle there of 64, which looks like our answer here is going to be D.